Alright everybody, so this is our first office hours video, if you want to call it that, where I'm going to try to review a topic that most of you reported was unclear from your reflections. And so this topic is going to be focused on pKa, pH, buffers, everything related to that. We're not going to do Henderson-Hasselbalch because, again, I'll never ask you Henderson-Hasselbalch questions myself. For those of you who feel you need preparation for that with the MCAT exam, please schedule an appointment with me and I'd be happy to do that with you one-on-one. But we're more going to focus on the material that I would expect you to understand in any future exam. So a lot of times we've been using the HA kind of shorthand for acids, but let's not do that this time. Let's instead use a real acid example like hydrogen chloride. So hydrochloric acid is a very strong acid. That means it donates this protein very, very readily. So we can imagine a beaker full of some solution. And let's imagine that that beaker, that solution, is actually very, very acidic already. So it has a lot of free protons already in it. The free proton concentration is quite high. That's what makes it acidic. So we can say the concentration of protons is high, and if that's the case, then that means that the pH of that solution is inversely related. The pH is low. So let's take some hydrochloric acid, which is a strong acid, of course, because it's quite dangerous, and let's take that hydrochloric acid and throw it into this solution. Now, if hydrochloric acid is a strong acid, that means that it dissociates readily. It doesn't really like having that proton, so it donates that proton quite readily. That's what a strong acid is. A strong acid dissociates easily. So even though there are a lot of protons already in this solution, even though the pH of this solution is very, very low, even though the hydrogen crowdedness in that solution is very high, there's a lot of hydrogens there, as soon as you drop hydrochloric acid in, it will dissociate into free proton and chloride ion because it's a strong acid and it readily dissociates. So the pH will continue to drop even further because we added free proton in there. So we've got a few things to consider here. Hydrochloric acid is a strong acid. It dissociates readily. That's fine. Because it dissociates readily, hydrogen chloride will donate a proton even in an acidic solution with a low pH because it dissociates so readily. That's fine too. But we measure that rapid dissociation by pKa. So we can say that hydrochloric acid, or hydrogen chloride, has a low pKa, which means that it dissociates into free proton very, very readily. If we use the same kind of relationship that we had for pH, a high Ka, which means a high dissociation, an acid that really gives up its proton readily, leads to a low pKa, just like a high proton concentration leads to a low pH. So now we've got a solution with lots of proton already in it, and when we add strong acid, that strong acid will dissociate as well because of its dissociation constant, because of its low pKa. Take it the other way, acids with low pKa's give up their protons very readily. That makes them strong acids, and they will give up that proton even in solutions that already contain a lot of free proton, in solutions that are already acidic. So that's the general idea of pKa and how it's related to dissociation of acids and the strength of an acid. Let's attack the same principle another way, though. Let's take the Henderson-Hasselbalch equation in its simplest state. And we'll say that the pKa equals the pH. Look at me, I've got it wrong myself there. So let's back up 1 second. Sorry about that. It's the pH equals the pKa plus the log of the dissociated acid. Let's keep our example straight here. Over the undissociated acid that's left after the dissociation. So if we consider a situation where the amount of hydrochloric acid that we've added some of it dissociates, and some of it does not. So we've got HCl, some of it dissociated, some of it still in the form of HCl. If we imagine a situation where these amounts are equal, in other words, half of the hydrogen chloride that we've added has dissociated, and the other half of the hydrochloric acid we did not, we would see that the amounts of this and this are equal. So in other words, if we started with 10 millimolar hydrochloric acid and it went to 50% dissociation, half of that 10 millimolar hydrochloric acid will have dissociated into proton and chloride ion. The other half would have remained undissociated. So we have equal amounts of each. Let's go back up to our Henderson-Hasselbalch equation and fill in some of these numbers. We would have 5 millimolar chloride ion because of that half dissociation. And we would have 5 millimolar undissociated acid. So these two values would cancel each other out. And we are left with the log of 1. So when we have 50% dissociation, when half of an acid that we've added to solution dissociates and the other half does not, the Henderson-Hasselbalch equation reduces to a log of 1. If you go into any calculator, even right now, and pause the video, and calculate the value of a log of 1, you will see that the log of 1 is equal to 0. So let me back up again. When you add acid to solution and 50% of it dissociates, that means 50% of it stays as an acid and the other 50% donates its proton, you reduce the entire log portion of the Henderson-Hasselbalch equation to 0. So that 0 is gone. So now we see that when you add an acid to solution and it dissociates 50%, the pH of that solution is equal to that acid's pKa. I'll say that one more time. When a solution is added, when an acid is added to solution and half of that acid dissociates to free proton and conjugate base, and the other half of that added acid stays the same, remains in acid form, you are in a solution where the pH of that solution equals the pKa. So what we typically say in biochemistry is when the pH of a solution equals the pKa of the acid you are adding, when that's the case, when the pH of a solution equals the pKa of the acid you're working with, you are at 50% dissociation. You know that half of the acid you've added has donated a proton and half of it has not. Now, hydrochloric acid is such a strong acid that it has a pKa of -7, which means if you had a solution that was at a pH of -7, which is not possible, you'd still achieve 50% dissociation. That's the fancy biochemical way of saying that hydrochloric acid will dissociate into free proton all the time. It's that strong of an acid. But if we imagine a weaker acid, like tris, we'll clear all this out. Tris, as a base or a conjugate acid, has a pKa of about 8. So what happens then is if we imagine that same beaker, and now it's a solution, and the pH of that solution is 8, if we have tris in that solution, the pH equals the pKa. So we know that 50% of this tris is dissociated and 50% is not. So 50% of that tris is a base, and 50% of that tris is an acid. It's at 50% dissociation. Now that base is a proton acceptor, and that acid is a proton donor. So let's imagine we have this solution of tris at 50% dissociation. The pH is 8, the pK is 8, tris is 50% dissociated. Let's add some additional acid to this. Some hydrochloric acid. That hydrochloric acid is going to instantly dissociate, because that's what hydrochloric acid does. But as soon as that proton is liberated, tris base is going to complex with that free proton and absorb it, complex with it, and thus neutralize it. So since that free proton donated by hydrochloric acid does not remain free for long, because it's gobbled up and neutralized by tris base, we see no change in pH. But it goes the other way too, because remember, we have 50% acid from tris and 50% base from tris in this solution. So let's add, instead of hydrochloric acid, let's add a strong base, like sodium hydroxide. As soon as sodium hydroxide is added to this solution, it dissociates, and that hydroxide ion really wants to raise the pH and make it more alkaline. But as soon as that hydroxide ion is liberated or dissociated from sodium hydroxide, it is gobbled up and complexed by tris acid. The conjugate acid of tris absorbs that free hydroxide ion and neutralizes it, so the pH doesn't change there as well. This is all due to the fact that we have 50% dissociation of our buffer solution. It's the base that buffers us from the addition of more proton, because that base is a proton acceptor. And it's the acid of tris that buffers against the addition of base, because it is a proton donor, neutralizing that base, turning it to water. Now, the last point we can make about this is that idea of breaking a buffer. So if we imagine that we've been adding hydrochloric acid to this solution again and again and again, we've continued to add hydrochloric acid, and we've added so much hydrochloric acid to this solution that all of our tris base has already accepted a proton. All of the tris base has essentially been neutralized and used as a hydrogen acceptor. If we continue to add free proton in the form of hydrochloric acid, there'll be no more tris base to absorb it, and those free protons will remain free. And because they remain free, the pH at that point will begin to crash. It will begin to decrease. And so buffers can be broken when all of the available base is used up as proton acceptors and can no longer accept additional protons, or all of the buffer acid has been used up as a proton donor and can no longer neutralize hydroxide ion. So there is a limit to how much these buffers can buffer. So that's pretty much it. We've got three main concepts to consider. One is that low pKa's are strong acids that dissociate readily. The second is that when the pH of any solution equals the pKa of the acid in that solution, we know that we are at 50% dissociation. That half of the acid we added remains an acid and has its proton still, and half of the acid we've added has dissociated into free proton and conjugate base. And finally, we ended with the idea of buffers, where buffers, by containing both acid and base in equal 50-50 levels, and they are equal because the pH of those buffers equal the pKa of the buffering agent. If we add free proton, that free proton will complex with base and be neutralized. And if we add hydroxide, that hydroxide will complex with proton from the acid and be neutralized. And so we avoid any changes in pH for a while due to the availability of both acid and base in this buffered solution. Hopefully that kind of clears things up. Again, this is the office hour style, so a little more informal, no pictures, just a general description and an overall explanation of the concepts that we're trying to understand. By all means, if things still remain unclear, you know how to get a hold of me. Stop by office hours anytime, and I'd be happy to hit this concept again.